Okay, nucleation of methane hydrates is a fascinating problem. It's been around for a long time, and there are a lot of reasons to try and understand this system. First, what is a methane hydrate? You can probably see a lot of other videos on YouTube to demonstrate things like this, where you have what looks like ice macroscopically, but it's flammable. And it's flammable because in the ordered structure of the water molecules, you have little pockets that are formed. So the waters are arranged with these little cages, and inside each cage there's a little free space, a little void, where a hydrophobic guest molecule can sit. So, for example, natural gas, methane, ethane, or CO2 can also sit in here, and in these cages they tile space in a way that fills space and looks much like a zeolite, if you're familiar with those things. And in here in this picture now, sort of zooming out just a little bit, you see the waters now are colored just red, and the bars here represent hydrogen bonds between adjacent oxygen molecules. So we're not showing the hydrogens anymore. And the guest now is just this little black united atom representing methane. And so this is structure 1 natural gas hydrate. There are also structure 2 and structure H and a few other forms. So so these hydrates are fascinating, one, because they are a massive fossil fuel reserve. So they're very difficult to tap, and they recently had a lot of press because a company in Japan figured out how to inject CO2 into hydrate reservoirs and get CH4 to come back up, right? So this was a long-term goal, and I think it's finally been demonstrated that this can actually occur. So this is driven, of course, because the CO2 hydrate is actually more stable than the methane hydrate is. So the CO2 pumped down at high pressure into a natural gas hydrate reservoir the natural gas hydrate will begin to disintegrate. It will give up the CH4. It will burp effectively, and you're now creating a CO2 hydrate reservoir. So this is both a way of sequestering CO2 and also a way of recovering methane out of these natural gas reservoirs in the form of gas hydrates. So note that the gas hydrate is actually more plentiful than all other fossil fuels combined. So in principle, if we could do this efficiently, there's a lot down there. And also it's quite common that hydrates are sort of a nuisance. They plug natural gas pipelines. They form at high pressures and low temperatures, which is exactly what you have when you're transporting natural gas and through a cold region like Alaska. So this, of course, can be quite a problem. Also, high pressures and low temperatures exist where you're trying to drill for oil in deep sea oil wells. This was illustrated, the problems associated with this were illustrated quite dramatically in 2010. Remember, there was this oil well blowout in the Gulf of Mexico, and when they were trying to cap the oil well, the wellhead, the hydrates were forming on the equipment and preventing them from making a good seal. And so basically, for all of these reasons, there's a lot of motivation to try and understand how methane hydrates form. And so many people, naturally, have thought about this in the past, and there are several different mechanistic ideas for how they form. The predominant mechanisms that have been put forth in the literature are this labile cluster hypothesis put forth by Dendy Sloan and coworkers at Colorado School of Mines. And that one says, well, I won't go through the details. Let me just point out to you that this is a homogeneous methane hydrate nucleation mechanism, in the sense that there's only methane and water in solution with each other involved in this process. There's no catalyst, no dirt, no sediment. Nothing is actually facilitating this hydrate nucleation mechanism in this story. Alternative ideas were put forth by Trout and coworkers in 2002. So they put forth this local structuring hypothesis, which is a little bit of a different sequence of events, but again, it's a homogeneous mechanism for methane hydrate nucleation. And yet another homogeneous mechanism for methane hydrate nucleation was put forth by Val Molinaro and coworkers. And this one basically looks like the two-step nucleation mechanism of Frankel and Tinwald in some ways, but without the metastable fluid equilibrium here. So this is also quite interesting, and we were looking at all of these different hypotheses that have been put forth in the literature, and wondering if it would be possible to use rare events methods to actually decide which mechanism is correct at which conditions. And there are many people thinking about this question, and rare events methods are particularly tough to use for these systems because they are two-component systems, right? So most of the rare events methods that we have work best when you have a single component structural transition. They don't work so well when you have a two-component system. You have to deal with the slow diffusion transport. You have to deal with also the structural transition that's happening. And of course, we don't really have even good order parameters to describe those things because the characters involved in the process are non-spherical molecules. Okay, so what people have done in many cases is to abandon rare events and go back to using brute force simulation methods. And in many cases, they're running their simulations at conditions where the system is so highly driven, the driving force is so large for nucleation, that nucleation will actually happen in just tens of nanoseconds of waiting time, even though the observation volume is only hundreds of cubic nanometers. Okay, so this is just astronomically fast. Now, a much slower and much more reasonable set of simulations were done in this paper. This is the group of the Colorado School of Mines. This is Dindy Sloan and Amadeo Sum and David Wu working with Matt Walsh. And what they did was quite nice. They have a bubble in their simulation box, and they're able to run NPT simulations this way and effectively control their supersaturation as the nucleation process is happening. So this was quite an innovation. And they can actually see with this framework that the induction times are on the order of microseconds, right? So they pushed this process to a point where it can now occur more slowly, and it occurs on about 100 times slower than other people had achieved. But it's still quite fast, right? So even though the induction time is typically about a microsecond before you see a nucleus form in this simulation box, the estimated rate that you get from looking at the size of their simulation box and the typical induction times is about 10 to the 26 nuclei per cubic centimeter per second. Now remember that the fastest nucleation rates that we can measure are on the order of 10 to the 21 nuclei per cubic centimeter per second. In a few cases, levitation experiments might be able to get out to like 10 to the 23 or so. But this basically is beyond the range of what can be tested. And it's also about 10 to the 30 times faster than the specific estimates that have been generated in conditions in the laboratory looking at methane hydrate nucleation. You know, their estimates there are like 10 to the minus 4 nuclei per cubic centimeter per second. So they're driving the process about 10 to the 30 times faster than what it typically happens at more realistic conditions. And so, you know, there's a good question whether you can look at the events that are happening in these trajectories and actually trust that they are representative of what happens at the much slower conditions where things happen in the laboratory or where things happen in nature. And that's not to say that the insights in this simulation are wrong. They are reflecting a process that's happening at a much higher driving force. Okay, so they're fast. Effectively, nucleation in these simulations is fast because the simulations are being run at an effective methane pressure of 32,000 atmospheres. Okay, so this is very, very high pressure. To put this in perspective, the Mariana Trench is about 1,000 atmospheres of pressure. So they're really, really, basically these conditions aren't accessible on the Earth's surface, and so we don't expect this to really be representative of what's happening in nature. And we set out with Val Molinaro. This is a graduate student of mine, Brandon Knott. I'm so sorry to Brandon. So Brandon Knott, working with Mike Doherty and Val Molinaro, we set out to really try and probe these nucleation mechanisms, and we came into all kinds of problems. First, we ran into the problem that it was very difficult to actually compute the supersaturation, right? So supersaturation is a key parameter in nucleation processes. It's like as important for nucleation as temperature is for chemical reaction rates. So we really have to be able to specify what that supersaturation is. And this is the trick that we came up with for computing it, right? So you can prepare a long, skinny simulation box. You have a layer of water in periodic boundary conditions that wraps through the back side of the box and comes out on this side. And we also have a layer of methane gas, okay? So what happens now is that as we increase the pressure, pushing from the two ends of our simulation box, we can increase the pressure on the simulation box. The concentration of methane in the aqueous part of this system goes up and up and up, resembling Henry's law. So this is the vapor aqueous solution equilibrium. And you see that it actually passes through and beyond the concentration of methane in the liquid phase. Once we go beyond about 100 atmospheres or so, we surpass the concentration of methane in the aqueous phase when that aqueous phase is in contact with a methane hydrate layer, right? So this is basically the two incompressible phases here don't respond to pressure at all, and the concentration just remains static, 100 millimolar, all the way across this large pressure range. So this now is the condition that we selected. We're going to work at 900 atmospheres, which does correspond to the bottom of the Mariana Trench, sort of an upper bound in pressure. We're going to work at 273 Kelvin. The reason we chose this temperature is to avoid a simultaneous driving force for ice nucleation. So many of the previous studies have been done at conditions that are about 250 Kelvin or 265 Kelvin or 225 Kelvin even. And at such low temperatures, it's not clear whether you should have nucleation of ice or nucleation of methane hydrate first, right? So, you know, the video that shows the Corona nucleating ice is a perfect example, right? That system, if you uncap it, can nucleate carbon dioxide bubbles, but it can also nucleate ice crystals. It's metastable towards both processes. And in fact, one process can interfere with the other process. And that's something that we really wanted to avoid. We wanted to have a situation where we only had a driving force at a realistic condition. So this is pretty typical out in nature. You find 273 Kelvin all the time. And we can find this pressure, at least in certain places on the Earth's surface. And so this is really a realistic condition where we know that we're actually able to prepare a metastable state here. So the studies that have been done at much colder temperatures, the starting point should probably be methane vapor in contact with ice, not methane vapor in contact with liquid, which is the starting point for many of those studies. So the starting point, of course, is quite important for getting a realistic representation of the process that's happening. If you start with the wrong phases, it's hard to argue that you're seeing the right things. So this gap now between the Henry's law-like curve here and the hydrate solution equilibrium curve here is the supersaturation. So at 900 atmospheres, when I have a vapor in contact with a liquid, this is the concentration of methane in that liquid phase. After nucleation occurs and it forms a hydrate phase, that concentration will then drop to the new equilibrium concentration, which is much, much lower. And the ratio between the concentration here and the concentration there is 5.8. That is my supersaturation, this S factor that you saw in some of the other nucleation works. So now what you would imagine is that why don't we just start with a system like this and study nucleation, the formation of a methane hydrate nucleus inside this aqueous phase, and do umbrella sampling and all of those things. Well, it turns out that those things don't work very well when you have a two-component system. There are reasons for that, and I will cover it in another video. You can read about them in JChem Phys 2011 paper that we wrote a few years back, if you can't wait. Okay, so what we did instead is to assume that our non-equilibrium trajectories of nucleation, so we can put a seed in the simulation box and we can watch how that seed grows as a function of time. And the average rate of growth, according to an overdamped Langevin equation, is related to the generalized driving force pushing the system to grow or shrink, and the mobility at the top, the mobility for growth or shrinking along that nucleus size axis. Okay, so this is basically what we've done. We've started with seeds of size 700 kgs here, and you see that we're beyond the critical nucleus size because typically these seeds now are starting to grow as a function of time, right? So this is time along the bottom axis, nucleus size along the top, but it's nucleus size in these average simulation runs, these dynamical off-equilibrium simulation runs. When you start with a seed of initial size 200, it initially begins to shrink, and right around the size of 300 or so, you see that we seem to be 300 to 400 seems to be in the vicinity of the critical nucleus size because on average these things are basically staying on top of the nucleation barrier. And notice that they stay up there for on the time scale of nanoseconds, right? They really take a long time to move. So this mobility is very small, and that's the reason that umbrella sampling is so slow. If you want to really think about it. Umbrella sampling requires that you be able to sample. Even if you can deal with the barrier, you have to have some mobility. And basically in this system, you have very, very little mobility. So now how can we compute this term? I already showed that back in one of the elementary slides on nucleation work. In fact, that was for this problem. So we've computed this attachment frequency by looking at mean squared displacement as a function of time at the top of the barrier. We can also identify this generalized force from classical nucleation theory. Okay, so here's the bulk driving force, and this is the surface contribution. So this one, actually, when the nucleus is small, can actually flip the sign of this term. So at very large sizes, this thing wants to grow. But when this term, when n becomes small, this term becomes very large, and it can actually drive the nucleus to shrink instead. Okay, and that's basically what you're seeing here in these trajectories. So there are a few unknown parameters here. We've got a shape factor. We've got an interfacial free energy. The shape factor, basically they're spheres, right? So I can show you pictures of what these nuclei look like, and I will in a moment. But basically they look like they're spherical nuclei. I've already shown you how we can compute the driving force, the chemical potential difference driving force. And we are using Val Molinaro's cluster size algorithm. So she can identify cages, and then we cluster adjacent cages to identify the size of our methane hydrate nucleus at any given time in our simulation. And this is the data. This is the way the data looks. It's basically data that represents the average size evolution as a function of time, starting from some initial condition. Okay, so what we're going to do here, we're going to take all these things that we know, and there's one thing that we don't, and that's the interfacial free energy parameter. And we're going to do a least squares fit on this data. So there's some value of the interfacial free energy parameter that should match all of these different curves that are going in different directions for a single value of the interfacial free energy. Okay, so that gives us 31 millijoules per meter squared. There are experimental estimates of the interfacial free energy for a methane hydrate in contact with aqueous solution that are 32 millijoules per meter squared. Can't get more lucky than this. I mean, clearly is an indication that we're doing something right here, but also the fact that these things really precisely align with each other, I think, is an indication that we got a little bit lucky. But nevertheless, now we know everything in our classical nucleation theory rate expression. We know the interfacial free energy, we know the driving force, we know the shape factor, and we can now plug them in to the prefactor and the barrier expressions. We estimate that the barrier is 305 kT, and using the classical nucleation theory, we estimate that the rate constant is then going to be 3 times 10 to the minus 112 nuclei per cubic centimeter per second. There's the confirmation that our nuclei are spherical. This is a picture of the nucleus at our estimated critical size of 350 kgs. Okay, so this is interesting because basically the rate that we got here is 0, right? So this is really, really extremely, extremely slow. To put it in perspective, if the entire ocean was in contact with methane at the pressure of the Mariana Trench, then and at 0 Kelvin, a single nucleation event would still take 10 to the 79 years. Now, even if you argue that classical nucleation theory makes errors on the order of 10 to the 20 or 10 to the 30 or so, you know, if I change this exponent by 30, I still have an astronomically long time. It's basically impossible for this to be happening, at least according to our results, it's impossible for this to be happening by any of the homogeneous nucleation mechanisms. So it must be heterogeneous nucleation, and of course that's a very, very difficult question to ask. And you know, heterogeneous nucleation can take many forms, and I think that quite a few people are now working on trying to understand what kind of heterogeneous nucleation this could be, looking at clay surfaces and graphite surfaces and things of that sort. So you should hear more about methane hydrate nucleation from this guy soon. This is a new graduate student of mine working on this problem, Jeff Poon, and he has a nice idea that we're just starting to develop now. So let me thank some key collaborators: Val Molinaro at the University of Utah, Amadeu Sum and David Wu at Colorado School of Mines, and also I want to thank Mike Doherty at the University of California at Santa Barbara, and Brandon Knott, who really did all the work. And Brandon was a graduate student at the time. Now he's working at National Renewable Energy Laboratory with Greg Beckham. And so thank you to all those people. And you can see a little review on some of the methods in this Advances in Chemical Physics article, and also some of these things, links to the Journal of the American Chemical Society paper where we published these results on our website. So those were published in 2012, if you want to do a search on that. And we thank the NSF for a computational discovery and innovation grant that supported this work. And of course, we're eager to pick up industrial sponsors. I think, of course, this is an area that industry has a lot to gain from, so hopefully they will notice this.